Even though the DeepSeek R1 paper is just a few weeks old, it already is quite influential in the AI world. This is because, well, the big labs, they've been experimenting with reinforcement learning for quite a while, but they didn't really publish information how to use it. And DeepSeek was the first big breakthrough paper which really explained what they were doing. So it's a very influential paper, and it's also pretty interesting. So let's dive right into it. So first of all, before explaining how R1 works, let's go through the first step, R10. So the basic idea of R10 is that you let RL run directly on the base model. So before, the usual steps were to pre-train your model, get a base model, then fine-tune this model with supervised fine-tuning, and then afterwards use RL to learn the reasoning. But instead of using supervised fine-tuning, they directly applied RL on the base model without any supervised data. And they used the group relative policy optimization algorithm. It's an algorithm they invented themselves. And the basic idea, if you're familiar to reinforcement learning, is to get rid of the critic, which basically predicts the value of a state, and replace this with just running the LLM G times. So if you have one prompt, for example, what is the solve this mathematical equation? If you just let it run one time, it probably doesn't give you the right result. But if you let it run 10 times or 20 times, because of the stochastic nature of the LLM, it will always produce a slightly different response. And in some instances, it may get it right or not. And this is what is shown here as the G. And the basic idea, everything else here looks pretty similar to PPO. So the basic idea is that you want to restrict the changes of each algorithm iteration. Like every time you update the model, you want to restrict those changes and keep them very minimal, because RL is quite unstable and you don't want to move too far from a working model. And the basic idea here is thereby to clip it. So the change of your new parameters divided by the old parameters should only be between 1 minus epsilon and 1 plus epsilon times the advantage. So usually the advantage is calculated by taking the reward and subtracting it with the state value. But because we don't have the critic, we don't have a state value. So here we just take the mean reward out of all prompts. Outputs. And then we divide it by the standard deviations of them to get a standardized advantage. The rest here is just a KAL divergence term. So we want to make sure that the new model architecture closely resembles the old model architecture. So the basic idea behind GRPO, it's a cost-driven idea. So is it more expensive to train a critic model, or is it more expensive to get G responses of the LLM for each prompt? And it turns out that it's cheaper to use an LLM now, and it will probably get even cheaper in the future. So it's an interesting approach. And also it has fewer moving parts. If you don't need to train a critic model, those of you who have worked in reinforcement learning before know that it's quite unstable and very brittle to hyperparameters. And if you just get rid of one model, it makes everything a bit smoother. So if you don't use any supervised fine-tuning anymore, you can just apply RL on infinitely many steps. You can just scale it with as much compute as you have, and you don't need to take into account how many humans you have and how much labeling costs, etc. However, for this you need to define like a fixed logic how to calculate the reward, and they do this with a rule-based system, which basically they only use questions in the first stage. They only use questions where they have a fixed answer. For example, if they say solve this equation and the answer is 3, they can just check if the LLM outputted the answer 3. They also used a format reward, which forces the LLM to put its thinking process between 2 tags. And as you can see in this graph, actually, the longer you let the RL run, the better the model gets. And it does so. Like it starting from 10% accuracy in the AIM data set up to over 70. If you use majority voting, you can even get this result. You can get another 15%. So you end up at 87%, which is even better than the O1 performance for this specific data set. But how does it really learn? Like, what does it do if you just let the RL work longer? How does it learn to make better results? It turns out it just produces longer thinking processes. So the longer you let the RL run, the longer the average response will get. And the model basically learns during this time to reflect. So it basically revisits and reevaluates its previous steps. When re-evaluating its previous steps, it also explores alternative approaches. And interestingly, in an intermediate model, it's called it even an aha moment. So the model tried to solve the issue or the problem. And at one point it said, whoa, wait, that's an aha moment I can flag here. Let's go back to the beginning and just do this and this. So this is very interesting. So it uses the same language as a human does, which is pretty cool, I think. Well, the results of R10 are that it uses or develops a strong reasoning capabilities, and it also develops these behaviors by itself. So reinforcement learning is a very good tool to really develop powerful tools and models to solve issues. But since it wasn't fine-tuned, it's completely unreadable for humans often. So it mixes the language, or it lacks, even though it has a reward specifically for the format, it still sometimes completely messes this formatting up. And also, RL is quite unstable, so the cold start phase when training the base model in the beginning is also quite unstable. And they solved this by introducing a 4-stage pipeline, which basically leads them from R10 to R1. So at stage 1, they collect a small amount of long chain of thought data. Chain of thought is when a model basically describes its thinking in multiple steps. So for example, if we all know these questions like how many balloons fit into this truck, for example. Then you just don't generate an answer like immediately. Usually what you think is you look at how big the truck is. You calculate or you approximate the volume inside the truck. Then you approximate the volume of the balloons, and then you try to approximate how many balloons fit into this truck. So it's a multi-step process. And they collected the same, with a similar logic, they collected chain of thought data as an initial data set. And then they used supervised fine-tuning to train the base model. So at this stage, they reintroduced supervised fine-tuning, even though they got rid of it before. And the advantages are that it's much more readable, it follows the output format much better, and it just has better performance than R10 because it just learns better. So DeepSeek say that following this approach of using supervised fine-tuning with a small amount of high-quality data set and then fine-tuning the model actually leads to fine-tuning the model and then using RL on it, like in an iterative approach, leads to much better results. Afterwards, after this first supervised fine-tuning stage, they use reinforcement learning as in the R10 stage. and where they again focus on well-defined problems. And since until now they've only used problems where they had fixed solutions, but they want the model also to be good in other domains such as writing or role playing and like just general tasks. Like how often do you give an LLM a math problem? Usually not that often. Maybe sometimes a coding problem, yes, but not. Other problems are very important as well. So for this step, they used also non-reasoning data and used supervised fine-tuning again. Just as a quick remark on supervised fine-tuning versus reinforcement learning, there was an interesting paper by DeepMind like 1 or 2 weeks ago, and they basically found out that using reinforcement learning lets the model really learn the intricacies of what's going on, while using supervised fine-tuning basically leads the model to just memorize what's going on. So if you have in-distribution data, it doesn't really matter. Then the supervised fine-tuning is pretty efficient too. It learns more quick than reinforcement learning. However, when you have out-of-distribution data, the RL can generalize, while supervised fine-tuning very quickly fails to achieve good results. But this is just a quick remark. And afterwards, lastly, after this supervised fine-tuning step, they again use reinforcement learning, this time to align the model with human preferences. So they use a second RL stage. For the reasoning data, they again use the R10 methodology, but for general data, they use reward models. They didn't use reward models before. So what are reward models? Reward models basically are, you can think of it, the reward models try to approximate how a human likes a solution. So if you give a prompt to an LLM and then you just let it generate 50 different responses, the reward model ranks those responses by how good or how well a human would like this response. The issue with reward models are that it's quite easy for the RL to trick it. So as you know, the RL is very good in finding creative solutions. So it just tries out lots and lots of different approaches, and sometimes it finds like nonsensical answers, so which doesn't make sense to humans, but which still generate good results just because the reward model isn't perfect. So they only use these reward models for the last stage to align the model better. So what you see here is an iterative approach. In stage 1, they use supervised fine-tuning. In stage 2, they use reinforcement learning. Stage 3, supervised fine-tuning. Stage 4, reinforcement learning again. So they cycle through these two post-training options to get to really good results. So looking at the results across different benchmarks, you can see that the R1, DeepSeek R1 performs pretty competitively to O1, which is surprising given that O1 is a closed source, closed data set. Given that O1 is a closed model and R1 is open source, or at least open weights. So it's very nice that they published it, and it's very, very cool because you can just use it. The costs are much cheaper, and it's also will probably be used for many different use cases in a similar way maybe that Llama has influenced the LLM community so far. Well, as you can see in this leaderboard, it performs pretty well in English and also in math. It has some issues in coding, or it's a little bit worse in coding than O1, but only slightly. So it generally performs pretty well. So they also tested one other thing. So R1 is pretty expensive to run. It has 600 something billion parameters. But can you just distill the reasoning capabilities on a smaller model? So the smaller model can also exhibit these reasoning capabilities without needing so many parameters. And in fact, they can. So they used Quen, which is from Open Alibaba, and the Llama from Meta, and they distilled the knowledge they gathered with R1. So they used 800,000 data samples they curated with R1 to fine-tune these models using supervised fine-tuning. And as you can see here, this works really well. So the Llama 70B version performs better than O1 Mini in most cases. And apparently it also works even better if you then apply RL on these models again, but they don't publish the results. But apparently it works pretty well, so it's interesting to find out. I'm pretty sure there will be further research on this very quickly. But now you may wonder, is it also possible to just train a small model using only RL? So apply this R10 approach to a small model. And the answer is, it probably doesn't work as well. So as you can see in these results here, the distilled model works much better than the R10 approach across like all benchmarks. However, there's even more recent research-related work where a Berkeley PhD student used the R10 approach to train multiple Quen 2.5 models in the countdown game. So the countdown game is, you can think of giving the LLM a couple of numbers. For example, take numbers 3, 5, 10, and 27. And out of these numbers, you should make a target number 400, for example. I don't know if that's possible. I just made these numbers up. But you need to make an equation using plus, minus, multiply, and divide. And to really get good in this game, the RL or the LLM really needs to think. So it really needs reasoning abilities. And in their research, they found out that the 0.5 B model just guessed a solution. So it didn't really learn how to think. But from 1.5B onwards, the model actually started to learn. So it started to search, to self-verify, and like exhibited the same behavior as the R1 model. They also tested using reinforcement learning on the base model and on an instruct model. And generally, instruct works much better because it learns faster, its outputs are more structured, and it's more readable. The specific RL algorithm apparently doesn't seem to matter that much. So they used PPO, GRPO, and prime, and they didn't find a significant difference between them. So it's pretty interesting as well. So if you used to PPO, just use that. Even though it may be cheaper to use GRPO. So it may make sense to apply that. And also the cost to fine-tune the model is quite cheap. So for the 3B model with PPO, it costs less than $30. So it's 10 H100 GPU hours to apply RL in this model. So it's performed pretty well. Research like this can only happen because they really laid out what they are doing. And so other teams can replicate this approach and try different approaches and make better decisions. And iteratively, like the whole community itself improves based on that. So now the Berkeley PhD student found out that the specific RL algorithm doesn't matter much and you only need 1.5B parameter models. But then the next week, maybe a different student or a different researcher will find out something else. And this way, the whole community will is very active right now. So thank you very much, DeepSeek, for that. It's a really, really cool contribution to the open source community. So if you're interested in learning more about this and want to read further, I have some more paper suggestions which may be interesting for you. So the first one, all of them are linked in the description. The first one is LEMO, less is more for reasoning. And the key idea is that if your model already has a rich mathematical knowledge from pre-training, you don't need a big data set to unlock the advanced reasoning. They propose a methodology how to create a very efficient data set to do that. And it may be very useful if you combine that with the R1 approach. So if you use like a very efficient data set as a cold start data set, the model may learn much quicker than it otherwise would. The second paper I'd recommend you is Search R1, where basically the idea is that reasoning models often, when they explore their chain of thought and they think about things, at some point they often lack the specific knowledge to test if what they're thinking is correct or not. So this model proposes to give them search abilities. So the LLM can itself Google and check if collect information to check if its reasoning is correct or not. And the last paper I would recommend you to read is Scaling Up Test Time Compute with Latent Reasoning, where they basically show that LLMs can think in latent space. So before, we try to make the thinking and reasoning process transferable. So DeepSeek even introduced a reward for following readable patterns and not switching languages, etc. However, why should LLMs think in the same space as we do? Like, why should they think in English or German or any other language? Of course, it's nice if you can just read what the LLM is thinking. So this way we can make the model better, understand its behavior better, etc. However, for some problems, it may not be so useful. For some problems, it may make more sense to have a smaller model. And this way we can just let it think in latent space. So basically we let the RL create its own language to solve the problem much more efficiently. And thereby we need less compute, less tokens, and probably also smaller models. There are definitely some benefits to being able to read the reasoning process. So I don't think that they will replace reasoning models as they are, but it's a very interesting approach for some edge cases. So thank you very much. I hope this was interesting for you, and see you next time. Don't forget to like and subscribe. Bye bye.